Good morning, everyone. My name is Sarah Hoffmann, and I am a researcher at Biomark. And today I wanted to talk a little bit about a protocol that we developed to increase the accuracy and efficiency of habitat data collection at various spatial scales. And I just want to start by acknowledging my co-authors, Richie Carmichael, Mike Ackerman, Kevin C., Braden Lott, Toli Mackey, and Chris Beasley, who did the bulk of the work on this protocol. So the primary imperative behind developing this protocol was to find a more time and cost efficient way to collect high quality habitat data in a scalable manner. So what we were looking for is a way to circumvent those site level data extrapolations by pairing multiple data sources like rapid on the ground surveys, drone surveys, or any kind of remotely sensed data. And essentially what this does is give us a scalable way to approach multiple projects. So for example, if we are looking at watershed scale status and trend monitoring, we would rely more heavily on something like the drone surveys or the remotely sensed data. Whereas if we were more interested in those site level, something like a habitat restoration area, we can go in and get those detailed on the ground habitat data in a more efficient way. And essentially what we are trying to build here is a way to inform prioritization and implementation in a more efficient way. So starting with the most detailed level of effort first would be these rapid on-the-ground surveys, where the goal is to quickly move through these channel units, delineating as we go, and then taking habitat characteristics at that channel unit scale. And where this would be really valuable is where you are looking for that added level of detail at something like a restoration site. And the next level up from the rapid on the ground surveys would then be these drone surveys, which is a great way to collect reach or watershed scale habitat data without having those on the ground crews. And drone imagery can produce these really detailed and data rich georeferenced and scaled orthomosaics, which are these tiled images that you see wherever the snow is overlaid onto that satellite imagery. And this drone imagery can produce a number of products, including things going towards a three-dimensional approach, such as a high-resolution dense cloud or digital elevation model. So now we're looking at ways to pull more data from these imagery. And I'll talk about in just a second how we've automated some of those processes. And then the final and broadest scale approach here would be using any type of remotely sensed data. So the example I've given here is satellite imagery that's been stored and is being almost continuously updated to provide these watershed level trend monitoring efforts. And something that we are looking at here as well is being able to incorporate things like LiDAR. So just making sure that we're leveraging all of the available data out there to provide the best estimates we can in these fish habitat models. And while it's great that we are also, or that we're scaling the data collection, I think it's really important that we are considering how these data are going to be used and therefore making the analyses scalable as well. And so what we've done, this is an example of a habitat capacity estimation that is achievable basically from the channel unit to the watershed scale. And obviously, as you scale, we know that there is going to be a certain amount of scaling of that uncertainty as well. And something that we're working on right now is a sensitivity analysis to see how these estimates change when you add or remove these data sources like the on-the-ground sampling. So that's something that we're looking into right now. But at first blush, it gives us this really good idea of how something like these multiple data sources can be combined to produce a common currency throughout the watershed and at these different scales. So an example of how these methods can scale at one site, we can look at essentially the whole approach to habitat restoration from start to finish. So starting with prioritization, we can use reach or watershed scale capacity estimates to identify limiting factors and put those in context of the imagery to see where habitat restoration actions could have the most impact. And then when the restoration is ready to be implemented, we can also use those fish habitat restoration or fish habitat relationships to inform the actual restoration design. So what makes a good pool a good pool? And pulling from our imagery and our on-the-ground surveys to help design the restoration that would be most effective at that place. And then after restoration, we can use the same tools to estimate the capacity that has been restored and evaluate the effectiveness of the program. And this is a really great way to provide a rapid assessment of the restoration action. And the really great thing about using something like habitat capacity as currency is the ability to efficiently and more accurately measure that metric and compare between the two sites. And as we have been developing this program, we have started to incorporate multispectral imagery. So we're now flying a DJI M200 with a MicaSense Altum, which is a 6-band camera. So it has the 3 bands of visible light and then also a long wave infrared band, near infrared, and red edge. So this is not only giving us the ability to extrapolate additional data like NDVI, but where it's really helping is increasing the differentiation among the, for example, water and bare earth. That's really helping in our image processing algorithms. So we've been developing these automated protocols using different types of machine learning to increase the efficiency of image processing, both for the drone imagery as well as the satellite imagery. So what you're looking at here is an image that has been classified using a supervised random forest classifier. And what this can do is pull out water, vegetation, bare earth, and woody debris. And something that has really increased the effectiveness of these classifiers is that multispectral imagery, especially thinking about the ability to separate water from these other categories. So this is another example of that same supervised random forest classifier, which is a pixel classifier that's able to pull out all of the woody debris in these highly complex environments. And while we know that there's a certain level of detail that you are going to be missing compared to walking through these reaches and counting every single piece of wood and measuring, the amount of time and money that you're saving is equivalent to, weeks or months of on-the-ground labor. So there's definitely a trade-off here in the resolution of your data and what you're willing to spend for it. But being able to feed something like kilometers of river imagery into a processing algorithm like this, we see as being a really good way to look at those watershed scale habitat in a more detailed way. And something that we're working on developing right now is an object-based classifier rather than the pixel-based classifier that you saw in the past 2 slides. So this is using a mask RCNN to pull out objects. And if you look at just the right for a second, we've actually done this pretty successfully using coastal imagery. So this is the southeast coast of Florida. And we were able to train this RCNN to pull out manta rays, sea turtles, sharks, humans, things like that, with relative efficiency. And so, kind of taking that back to our project here in the Columbia River Basin, we think that this kind of object-based classifier could also be really used or really well used to pull out wood as well as something like reds in the river. So we're just starting on that project now to see how well these different types of classifiers are going to work in the riverine environment. So in addition to the time and cost efficiency of using this multi-data approach when we're looking at habitat analyses, Dash also has a great advantage as far as data visualization goes. So we're able to produce these quantitative habitat capacity estimations and overlay them onto that high resolution drone imagery. So what that's giving us is an added layer of context that allows us to go in and perform those qualitative evaluations. So do that eye test and see, yeah, these areas that have really high habitat capacity look like something that would have high habitat capacity. So it allows us that extra level of ground truthing. In addition to that, it produces these high quality data products that could be used for a variety of stakeholders, from funders to landowners that are interested in how actions may be enriching the environment, especially when we think about areas like restoration sites. And the final advantage that we see with the DASH approach is that it's producing this high resolution imagery that's being stored and curated in a way that researchers working outside of our immediate project, or maybe in 15 years down the line, can come back and access this standardized raw data source for whatever application they may need. Um, so despite all of these different efforts happening in the Columbia River Basin with a little bit of a different flavor on each project, imagery can kind of be that standardized currency that we all use, or that standardized data that we can all look back to and pull the necessary information out of. So it's a really nice platform both for data sharing right now, but then also setting up a bank of data as we move forward, and especially as things like imagery and analyses get better and more efficient. And so to wrap everything up, we really worked on creating Dash to find a more time and cost efficient way to collect high quality habitat data and conduct these analyses at multiple different scales. And we have found huge time and effort savings as we've rolled this out in the Lemhi River in Salmon, Idaho. And we've been able to scale the project at these different sites as we find those needs. Um, Also, as we've been developing these post-processing tools, we are just continuing to save more and more time by eliminating some of the labor needed to go through all of the imagery manually. And then the last project that we're really working on right now is developing a permanent database where this imagery could be stored and accessed by stakeholders in the project or additional researchers that's providing this infrastructure for long-term data warehousing, storage, and the ability to query the data that you need and see what work has been done in these sites already. Um, so with that, thank you for listening, and I would be happy to take any questions.